Okay, first of all, thank you very much for inviting me to such a nice place. Today, I would like to talk about sub-PeV gamma ray observation with the Tibet airshow array. Today, I focus on the gamma ray observation. Okay. Sorry. Okay. This is a joint experiment between China and Japan, long-term airshow experiment for more than 30 years. Sorry, this is the outline my talk. First, I will give some brief introduction of the cosmic ray and our experiment, and then I will show you the recent result, including some galactic diffuse gamma ray and some pivoton candidate. Finally, I will summarize my talk. Okay, so let me start with the cosmic ray spectrum. You can see the prominent break feature at 4 peta electron volt, which is rapid decrease of the cosmic ray, so-called Ni structure. It was discovered in 1958, for more than 60 years ago, by Krikov and Christiansen. And based on this observation and some theoretical consideration, cosmic ray below this energy believed to be accelerated in our galaxy, such as supernova remnant, galactic center, and star-forming region. However, there was no experimental evidence of such as accelerator. Here is an open question is in the cosmic ray physics. Pivatron, which can accelerate up to PeV energy region, really exist in our galaxy or not. This is our motivation. However, cosmic ray charged particle bent by the magnetic field in the universe and lose their original direction. So we cannot identify the origin using the cosmic ray itself. As a second approach, cosmic ray interact with the ambient interstellar gas around the accelerators and produce gamma rays through the neutral pion decay, which has about 10% of the apparent cosmic rays, so that sub-PeV gamma rays are expected if pivatron exists in our galaxy. So these neutral particles, gamma ray, can go straight in our galaxies, so we can point back to the cosmic ray origin. Okay, so next, the Tibet airshow array is located in Tibet, China, at 4,300 meters above sea level. This array consists of about 600 scintillation detectors with an area of 0.5 square meter, like this structure. And its covering area is about 66,000 square meters with 7.5 meter spacing. And as you know, the primary cosmic ray or gamma ray interact with the atmosphere and produce many secondary particles, so-called air shower, mainly electron and positrons. And we can reconstruct the primary energy from the particle density of these secondary particles. And also primary arrival direction is also determined by the relative timings of these secondary particles. Our angular resolution is about 0.2 degree for the 100 TeV gamma rays. And energy resolution is estimated to be 20% for the 100 TeV gamma ray. Okay, so left figure shows the typical event display, a real gamma ray candidate. Here, color scale represent relative timings recorded in each detectors, and the circle size proportional to the logarithm the number of detected particles. And this red arrow indicates reconstructed core position and arrival direction. And the primary energy estimated from the lateral distribution, right figure, fitted by the NKG function. Here, we refer the new energy estimator S15, which is particle density at the distance of the 50 meter from the air shower axis, which is significantly improved energy resolution in this energy region. And this event is energy estimated to be 250 TeV with around 20% uncertainty. And then next, let's move on the water Cherenkov muon detectors to discriminate gamma ray signal and cosmic ray background. We have now a total 3,400 square meter water pools under the ground air shower array. And each pools divided into 16 units. Each unit has about 50 square meter in area and 1.5 meter in depth water. This figure shows the side view of the one unit. As you can see, each unit has also down-facing 20-inch diameter hot multiplier tube and inside concrete wall covered by white type sheet. To correct reflect Cherenkov light produced in the water. And as you know, the muon component can penetrate into deep underground. On the other hand, electromagnetic component absorbed by the here 2.4 meter soil overburden. So this kind of detector can measure the almost pure muon component. Okay, in this slide, I demonstrate the number of muons measured by underground detectors, vertical axis, and horizontal axis air shower size measured by the ground detectors. And red figure shows the gamma ray Monte Carlo simulation, and right cosmic ray data, and color scale represent the number of air showers. And null zero muon events are plotted here, very important. You can see these null muon events are dominant in the gamma ray induced air shower. On the other hand, cosmic ray induced air shower have much more muon. With this difference, we can separate them. And here you can see the solid lines indicate the optimal muon cut line to maximize signal to noise ratio, assuming the point-like sources. As a result, we have succeeded in the cosmic ray background to the reducing cosmic ray background to the 10 to minus 3 above 100 TeV energy region, while about keeping about 90% gamma ray. This is estimated by Monte Carlo simulation. Okay, then here I will show you the first result of the ultra-high energy gamma ray from the Club Nebula, published in 2090s. Left two figure shows the gamma ray image around the Club Nebula, above 10 TeV and 100 TeV energy region. And the maximum energy reached 450 TeV at that time. And this was first detection of the sub-PeV gamma ray with more than 5 sigma. And left two panels show the so-called theta square plot, some distance from angular distance from the Club Nebula. Our observed distribution completely agreement with the Monte Carlo simulation, assuming the point source. And next, let's move on the diffuse gamma ray analysis. To extract a small diffuse gamma ray signal embedded in the huge cosmic ray background, we adopted a tight muon cut, which is just one order of magnitude tighter than the standard analysis, as shown by red lines. As a result, we succeeded in the reducing the cosmic ray background 10 to minus 6 above 400 TeV energy region. And then here I will show you the gamma ray-like events distribution after the tight muon cut in the equatorial coordinate. Blue point shows the observed event arrival event distribution in 3 different energy range. Upper one is between 100 TeV to 160, and middle one 160 to 400 TeV, and the bottom one above 400 TeV. And you can see that some events concentrate on along the galactic plane, as shown by solid curve. And at the highest energy region, so 38 events are survived in our field of view after the tight muon cut, almost background free, you can see. Among them, the 23 events are located within the galactic latitude less than 10 degrees. Okay, then as shown here, the latitude profile, galactic latitude profile. Red point shows the observed data across our field of view, including source contribution. You can see the clear peak is seen at the galactic plane in different energy region with a high statistical significance. Compared with the gray shaded histogram modeled by Lipari and Barnett, assuming the hadronic scenario. Okay, then as shown here, the energy spectrum of the ultra-high energy diffuse gamma ray. Upper panel shows the energy spectrum in the inner galaxy region. This target region completely same as the previous work by the Argo YBJ blue point around 1 TeV energy region. And red point shows our observed data after the excluding contribution from the non-TeV sources. And then these measured flux are compared with the diffuse gamma ray model, assuming 2 different hypotheses in this paper. One is a cosmic ray spectrum is identical in whole galaxies, solid curves. The other one is a cosmic ray spectrum is harder, getting closer to the galactic center, dashed curve. Our measured flux are overall consistent with both model, assuming the hadronic scenarios. And lower figure shows the outer galaxy region was searched by the Casimir experiment long time ago. Our data measure our data reasonable agreement with the models, except little bit enhancement highest energy beam. And then here I would like to mention the Cygnus Cocoon region. We first time claimed this high energy event around the Cygnus Cocoon region above 400 TeV energy region. This is a gamma-like distribution above 400 TeV. You can see the events as seen along the galactic plane like this. Among them, we found 4 events within the some radius circles from the Cygnus Cocoon region. And these events can extend energy spectrum up to the 1 PV energy region. Our flux plotted here. So already Russell collaboration reported more detailed spectrum, but our spectrum also consistent with Russell spectrum. And then I will show you the recent Russell diffuse gamma ray measurement compared with our result here. Red point shows the Russell flux. This is a little bit, not a little bit, a few times lower than our flux, but we cannot directly compare with each other because Russell collaboration masked much more region along the galactic plane like this. However, our measurement may include some unresolved point sources. So we checked that. As you know, the Russell collaboration reported more than 40 ultra high energy sources. Here we compare the first Russell catalog and Tibet diffuse events. Blue circle shows the Russell ultra high energy sources, and red point shows the Tibet diffuse event. Surprisingly, our diffuse event not coincided with the Russell sources except Sinus Cocoon region. And this is ice cube diffuse neutrino result recently published in science paper. They detected diffuse neutrino flux along the galactic plane at 4.5 sigma level. And in this paper, they claimed ice cube neutrino flux smoothly connected to the neutrino flux estimated from our measurement, assuming the neutral pion model best fit flux. It's a very strongly supports cosmic ray origin of our measurement, regardless point source or diffuse. And then next, let's move on some pivotal candidate. First one is a very famous one, SNRG-106. This is the energy spectrum extended up to the 100 TeV energy region. Red point shows our measured spectrum. However, this measured flux can be explained by a hadronic scenario and leptonic scenario without any other wavelengths data. And left figure shows the gamma ray image. The gamma ray excess is very coincident with the molecular cloud shown by black contour and cyan contours and SNR. However, our gamma ray excess is shift from the pulsar. This is a support hadronic scenario. So if we assume the hadronic scenario, the proton cutoff energy estimated to be 500 TeV energy, and the proton total energy is 5 times 10 to 47 ergs, assuming the distance 800 parsecs. And this source MAGIC also reported gamma ray signal SNRG-106. They found high energy emission between 6 TeV to 30 TeV, which are consistent with our result. And they also investigate multi-wavelength energy spectrum, including X-ray observation. Their spectrum fitting support favors hadronic model because this X-ray observation constrain somewhat leptonic scenario. Okay. So next candidate, Hess source is J1843-033. This is a very similar situation to of the previous G106. The gamma ray spectrum extended to the 100 TeV energy region, and our gamma ray excess is coincident with the molecular cloud and SNR. If we assume the proton acceleration in this source, the proton cutoff energy is 500 TeV, and the proton total energy is about 10 to 49 ergs, assuming the distance 9.6 kiloparsec. And next candidate also has source J1849. This is published in APJ, which is a middle-aged pulsar nebula. But we cannot find any SNR candidate around here. The gamma ray excess also coincident with molecular cloud. Little bit difficult to see the green contact here. And energy spectrum looks very flat. If we assume the hadronic scenarios, proton cutoff energy estimated to be well beyond the PeV energies, and the proton total energy 10 to 49 ergs if we assume the distance 7 kiloparsec. Okay, so let me summarize my talk. We successfully observed the ultra-high energy diffuse gamma ray and some pivotal candidate. And now there are a lot of ultra-high energy sources mainly discovered by Russell experiment. However, there are no sub-PeV instrument, wide field of view instrument in the southern hemisphere. So next step goes south. Some projects are ongoing or planned, such as alpaca, mega alpaca, SWGO CTA, and as well as some next generation neutrino experiment. Next session, Marcos and Zorena will give some status of alpaca experiment. Okay, so this is a conclusion of my talk. Tibet S gamma experiment successfully observed the ultra energy gamma ray from the Club Nebula for the first time and opened the new energy windows. And we also successfully observed the galactic diffuse gamma ray in the sub-PeV energy region first time. And the ultra high energy Tibet diffuse events do not coincide with Russell ultra high energy sources. And ice cube diffuse neutrino flux smoothly connected to our measurement, assuming the some neutral pion best fit model. And finally, we found also some pivotal candidate associated with dense molecular cloud. However, it is very difficult to distinguish leptonic and hadronic from the spectrum shape alone. So some morphological study and some constraint from the X-ray observation very important. However, maybe in the near future, next generation neutrino experiment give us more conclusive evidence for these promising pivotal candidate, I hope. Okay, thank you very much. That's all from me.
Thank you very much for this nice overview and the interesting results and respecting the time on to the second. I'm impressed. Okay, there's comments and questions. Yeah, Sunil?
Yeah, I'm just intrigued by this comment that Tibet ultra high energy events above 400 TeV do not originate from LASO ultra. Is it because the angular resolution is good enough for you to distinguish between these two regions?
Of course.
So what could be the possible cause of, that you see it and Lasso doesn't see it, and Lasso sees it and you don't see it? So I find it a little bit puzzling that, the two sources nearby and each group sees a different source. So what could be the possible cause of?
But Lasso sensitivity is better than, much better than our instruments. So maybe Lasso, not possible. Lasso missed some.
But then they should see the source you see also, right?